you'd have to have a printer capable of printing 100,000 dots per inch. Yes? And if you drew the atom so large that you could actually see the nucleus, it would be so large you couldn't see the atom. You couldn't see all of the atom. Right? You can't draw a picture of an atom. The nucleus is so small. Now.
Well, you can't draw with the scale.
Yeah, that's right. You can't draw it in a way that you could see it. Right? Now, in that atom, what's in the atom?
All the mass.
Well, almost all the mass. There's neutrons and protons, correct? Neutrons have no charge, right? And they're little spheres. Neutrons are little spheres. I think they're gray, and they've got a big N stamped on them, right? Protons, a little P plus there, right? Okay, on there, and they're blue usually, or red. They could be red. Some of them are red. You know, it depends on where you buy them from. Okay, now in the nucleus, those guys are scrunched up. The point is they're scrunched up very close together. There must be a force binding them together. Yes,
gravity.
It must be a strong force.
Recipe.
It must be a strong force. It must act only in the nucleus and not outside the nucleus, because otherwise it would collapse all matter. What force do you suppose that is? It's the strong nuclear force. It's very good. I notice none of you said weak nuclear force, right? When properly prompted, right? Okay, now, here's the deal about this, is that it's very strong, but it's also very short range. Once you start to get much bigger than sort of, I don't know, 10 to the minus 15th-ish in size, okay, it starts to lose effectiveness. Now, have you wondered why there's not an infinite number of elements? Why can't we just go out to element 300? We've got all the protons, let's just stuff them together. Why do they fly apart? Why are they unstable?
The bigger you get, the weaker the strong nuclear force is.
The bigger they get, the weaker the strong nuclear force is. Did you guys understand that?
No.
Why? Well, because strong nuclear force is short range. At some point, the nucleus outgrows the ability of the strong nuclear force to exert a force on itself. That's all right. So let's draw a picture of a big nucleus. Right? Here's a big nucleus. This guy's so big, right, that this part of the nucleus can't exert a strong nuclear force on this part. Yes? Right? So at some point, they get too large. So if you look at that top limit here, every dot here is an element that is stable, right? And so this is element number here. This is protons. And then the fact that there are different numbers up and down, those are the isotopes, right? If we go here, right, this is neutrons equals protons. N is neutrons, Z is protons in physics language, right? That's neutrons equals protons. At this very limit right here, notice that it just ends. It ends because the nucleus got too big. Now, nuclei before you get there, when we're talking about like uranium and those guys right in here, right? If you're talking about uranium, is uranium there? Yeah, uranium's like 92 or something like that, right? Okay, uranium is it's got crazy, the nucleus is crazy. It's not a hard thing. Like helium's, the nucleus is very tightly bound. Uranium, it's like there's the Coulombic force that's pushing apart the protons is just about evenly matched with a strong nuclear force. And so the nucleus is actually sort of blousy. Yeah? It's sort of, in fact, neutrons in a nuclear reaction often are going so fast that they'll zip right through the nucleus and not react. Have you heard of moderators in nuclear reactors? Moderators are things that slow the neutrons down. You've got to slow them down so that the nucleus can hang on to them, ingest the neutrons, and then split apart, right? So these nuclei are getting less and less tightly bound. At this end limit there, they fall apart. They're so big that they fall apart. It's like my kids when they were little. We used to pick up these cardboard blocks, and they'd be standing there, and I'd hand the blocks to them, and they keep picking them up in their arms, and I keep handing them blocks, right? At some point, the little like 2-year-old, 3-year-old arms could only carry so many cardboard blocks, and then they just fall down, right? As a parent, you've got to find like fun things to do that entertain you as well, right? And they'd be trying to hold all the blocks, but they just couldn't with their little arms, okay? Why is it, and then one last thing, I can explain one last thing with this. What's happening to the number of neutrons relative to the number of protons as you go up?
It goes up by a lot.
What's going up more, neutrons or protons? Yeah, heavy elements have way more neutrons. Why?
They need more of them to stabilize.
Protons repel, neutrons do not, right? So a stable element, as you get bigger and bigger, has to have more neutrons that don't rip it apart than protons that do rip it apart.